Good afternoon, everybody, and welcome to the first event of the Loddon Plains Future Farming Regen Ag Group. I'm really excited to present this to you today and get things up and running for the group. Welcome to everybody and thanks for coming along. Just a couple of housekeeping things to begin with. If everybody could please turn off their video and mute themselves. It looks like everybody's pretty down with the Zoom etiquette nowadays. That'd be really great. It just saves bandwidth and saves problems on everybody's end, everyone's ends. So if everybody could do that, that would be great. To kick off, I'd firstly like to acknowledge the traditional owners and custodians of this country and the land on which we meet today. For me, and for Beck, that's the Dja Dja Wurrung people. I'd like to acknowledge the rich living cultures, traditions and connections of Aboriginal and Torres Strait Island people and their intrinsic connection to the land that we live and work on. And I pay my respect to elders past, present and emerging. I'd like to extend that to anybody joining us today. I'd also like to particularly acknowledge the Dja Dja Wurrung, Barappa Barappa and the Wamba Wamba people, traditional owners of the land on which I live and that I work, and I extend that to the land which you're coming from today and the traditional custodians of that land. So a quick introduction to the Loddon Plains Future Farming Group. This is a group to support like-minded farmers in developing adoption methods and practices in regenerative and sustainable agriculture with some key kind of objectives to improve knowledge of soil health and structure and looking at improving knowledge of growing and utilising grasses and pastures for livestock and maintaining ground cover and looking to increase native vegetation on farm, either in standing kind of woody carbon and standing kind of areas or also in native pastures and the like. If you'd like to know more about the group, I'll be throwing a few links into the comments and the chat that you can have a bit of a look at and click through to, and I'll also put a registration in for the group to keep in touch as well. Now, with all of our housekeeping done, I'm going to throw you pretty quickly to Rebecca Mitchell from Agriculture Victoria. Beck is here to talk to us about understanding our soils today and is a soil specialist working with Ag Victoria and with farmers across the kind of central Victorian region. So I'll hand it over to you, Beck. Welcome and thanks for your time. And I'm looking forward to what you've got in store for us for the next hour or so.
No worries. Thanks, Danny. And thanks everyone for spending the time to come along and hear a little bit about soils. So unfortunately we can't be out in the paddock, but hopefully you can see behind me I've tried to bring a little bit of the paddock to us, so we can pretend that we're in a soil pit and we're able to touch the soil and smell the soil and do lots of things like that. So I'm really excited to chat to you today. So I'll just get my screen sharing happening and we will kick off. There we go. So hopefully that's looking good for everyone. So as Danny said, I work for Agriculture Victoria and going to talk to you about understanding our soils. So to kick off, I'll share a little bit about myself. I have been working in the soil space for approaching 10 years now, and I love to do all things soil. So I love to talk about soil on the radio, I love to go to soil conferences, I love to paint with soil, I love to eat soil cakes. I like to do soil research out in the paddock, taking calls, looking at what's going on. And most importantly, I love chatting to farmers and landholders and anyone who'll listen to me talking about soil. So big thanks for coming along today and hearing about that. So in terms of if you've got any questions as we go, feel free to pop them in the chat and we'll get to them as needed. So yeah, feel free to do that. And there'll be a few questions that I'll throw out to the group. So feel free to put your answers in the chat, or you can keep them to yourself and see how we go. Wonderful. So the first question I want to ask everyone, and yeah, like I said, feel free to pop them in the chat, is what first comes to mind when you think of soil? And I've got a few picture prompts there. Yeah, so feel free to chuck them in and share your soil thoughts. So we've got earth. Yes, that's a great one. Soil is earth. Food. Soil helps give us our food. It's a place for plants to grow. Life, a living organism. Fantastic. So growth medium, soil is so many things, and a lot of us will have a different understanding of what we think about soil and how we treat the soil. So the way that I like to think about soil is I like to think of it as a biological entity, so something that's vibrant because it's got so many organisms that are alive, that are full of activity, doing lots of things in the soil. It's also something physical, so it's the way that the soil forms together or is made up can provide the structural support for the water and the plant nutrients that are required for everything to grow. It's also, it's a chemical component as well. It's got the minerals and the nutrients. That's where all of those are stored for our plant growth. So essentially, it's the lifeblood of the land, the farm, the garden, the food, the fibre, all the things that we're a part of and are so strong in our world today. So what we're going to cover today in this, I guess, first session for the Loddon Plains group in soils is, so what is soil? What's a healthy soil? Why would you do soil testing? How can you take a soil sample on your farm? And what are some more resources for understanding soil tests? So we're going to wind back all the way back to the start, so a long time ago, and how is soil formed? So soil starts by the breakdown of rocks, the granites, the sands, the basalts and the shales, or it's the accumulation of sediments through wind or water processes as they move across the land. So it's something it's always happening. Soil is always forming, and it's developing through physical, chemical and biological processes of weathering, helping that to happen. So it's something that takes a long time historically to form the soil that we have today. And you know, there's the figure that gets thrown around is that in 1,000 years, it can just 1 to 5 centimeters of soil is formed. So that's 1.1 millimeters a year of soil that were actually being formed through the natural processes of that biological, chemical and physical weathering. Now, of course, the different farming practices that we do or how we treat our soil can help increase the rate that soil is formed, or it can actually decrease the rate that soil is formed by losing soil. So we'll touch on all those things today. One big way I like to think of soil, so bar being this chemical, biological and physical entity, it's stuff and it's the things in between the stuff, so it's those spaces, and we'll touch on this all the way through the talk today about how and why that's important. So when we're thinking of what is soil, so in kind of a typical clay soil, you've got 45% of your minerals. So that's from the breakdown of those sediments and rocks that we talked about. You've got 25% water, 25% air, and then 5% organic matter. That organic matter is broken up into the living organisms. You've then got your roots and your crop residues, and then you've got the span of the dead and decaying organic matter in the soil, from really big pieces to our pieces that are inert or resistant, like our charcoal. So that's a kind of a typical clay soil. When we think of a sandy soil, it's a little bit different. So a sandy soil has a lot more mineral component, similar amounts of air, but less capacity for water in a sandy soil, and typically less organic matter is held in a sandy soil. So that's soil. So what makes a healthy soil? So it's something that's physically, nutritionally and biologically balanced to be productive and stable. So it's about a soil that is robust and can withstand how we treat our soil and the things that we do to change the soil. So in agriculture, that's making sure we're not losing our fertility, we're not ruining our structure or impacting our biological activity by the things that we're doing when we're growing our food and our food for us and our food for our grazing animals too. So understanding, monitoring and managing soil health is the basis of what regenerative farming is all about. Getting the soil right and looking after it and making sure that it's managed to balance and keep it stable and productive. So how can we actually understand if we have a healthy soil? And the North Central CMA developed a soil health guide to help send us through that journey about things that we can do to understand soil health. So there's 9 indicators of soil health, and it's information that can help us understand any soil health issues that we might have. And it's a physical book. It's also an online book, and it can help us step through the visual tests that we can do in the paddock or at the garden at home to understand what's going on. So I'll pop that link in the chat to where it sits online. And that's the online version. If we're together, I'd be able to give you a physical book, and hopefully that will be able to happen down the track and you can get a hard copy of that. So let's get into it. So what the soil health guide covers is ground cover, soil biology, colour, pH, texture, topsoil, structure, compaction and stability in water, which is flaking and dispersing. So let's start with ground cover. So ground cover is important for soil health because it's something that we can actually influence ourselves, and that's by how we manage our grazing and our crop management, and also through the species selection that we choose. So we can really strongly influence how much ground cover we have on our paddocks. When we're talking about ground cover, it's the living and the dead plant material that covers the soil. And that's important to remember. Ground cover is really important because it holds the soil in place and reduces erosion, whether that's from wind and water. And a lot of the really important nutrients, the organic matter, lots of things are held in that topsoil, and we want to make sure that we're holding that in place. It also promotes the soil microbial activity that helps the plants provide their water and their nutrients, and it also increases organic matter. So I've got a little activity for us. The first activity that we've got is I want you to get a pen and paper or just something that you can write down, and we're going to do a little bit of an estimation of ground cover through pictures. So it's really important to be able to look at the paddock and go, how much ground cover is there? And that's for pastures, and it's also for crops as well. So it's important that we're maintaining that 70% ground cover across the year. And a lot of management decisions that we can make can influence that, as we touched on earlier. So let's get into it. Let's see how good your eyes are at guessing the ground cover. So this is our first picture, and this is a rolled stubble. The second one is a mixed pasture. The third one is a standing stubble. The fourth one, option D, is another pasture. E, we've got a standing stubble. F, we've got another pasture. And our last one is another standing stubble. So as you can see, a lot of those pictures look the same, and we'll just see how, oh, sorry, one last one. There we go. I forgot about that one because that's not what we want to see. That's clearly less than our 70%. So let's go through the answers, and you can see how you've gone in estimating ground cover. So the first one was 70%, and the second one was also 70%. So that's what 70% looks like in a stubble and a pasture. Then we've got a standing stubble, 90%, 40% ground cover, 30%, 90% in a pasture, 40%, and 20%. So how did everyone go? It can be harder than you think to guess it, but hopefully everyone at least can now take home that this is kind of what we're looking for when we're thinking about 70%. Yeah, there we go. We've got a comment that the stubble got me. The stubble is hard, and when we're also thinking about the stubble cover, what stubble does is it protects the soil as well, because if it's a standing stubble, then when the sun comes on the stubble, you get the shadow effect as well, which protects the soil in terms of temperature, but it also can collect more soil when soil moves across it. So the stubble one is very difficult and tricky. So in terms of the importance of ground cover, in keeping soil where it is and all of those things are important, but it's also about promoting the buildup of organic matter into the system. So the more plant biomass that we have that's grown, the more organic matter that we put into the system. So increased biomass, increased root growth, and increased biological activity, because the plants are cycling through, providing more energy for everything underground. With that increased biomass, we've also got reduced soil erosion and reduced soil carbon loss. When soil erodes, it takes the carbon with it and releases it into the atmosphere as carbon dioxide, and that gives us reduced emissions. So there's lots of benefits about increasing our ground cover. The organic matter inputs into the soil and the turnover are influenced by lots of different factors. So how we get that soil organic matter into the soil is determined by the texture. So actually how much clay there is, because the clay is the part of the soil that holds on to the organic matter. The climate's a big determination about soil organic matter in terms of how quickly things will cycle. The warmer things are and the more rain there are, the quicker things will turn over. And as well, the management. So how we graze it, how it's covered, the species there, the amendments that we put in, such as our composts and things like that, all affect organic matter. There's lots of different fractions of soil organic matter, and I don't want to get too deep into this because soil carbon could be a whole another 2-hour webinar itself just talking about carbon, but and organic matter. But when we're thinking about soil organic matter, there's the different fractions, and they all are turning over and have a different length of life in the soil. So we've got the soil that's the carbon and the soil organic matter that turns over really quickly, you know, in terms of hours or days, and then we've got the labile organic soil organic matter component that takes 1 to 5 years. Then we've got the humus, which takes the 20 to 40 years, and then we've got that stable or resistant organic carbon, which is in that form, which takes a much longer, 500 to 1,000 years to turn over. So this soil organic matter is continuously cycling through the system between the living, the decomposing, and the stable fractions in the soil. So as you can see, it's really complex and there's a lot of things going on. In, I guess, a simpler way to think of it is you've got your inputs into the system. So you've got your plants and your animals. So when they're putting their manures into the system through their byproducts, or when the plants or animals die, and that's including the microbes and the soil biology in the system, that is the fresh residue. So it cycles through and gets transformed, and the organisms break it up and they're consuming the organic matter and they're turning into lots of different forms. And then it gets broken into even smaller pieces then. We can see some of that nutrient from the organic matter is released into the system. So that once it's starting to be decomposed and broken down, it becomes available to the plants in terms of nutrients. This is also how it gets lost out of the system into the atmosphere, but it breaks down and goes into the humus proportion, and then it starts to get more stable and becomes in that resistant form. So all these cycles are continuously happening in the soil. So how do we get from soil organic matter to organic carbon. So soil organic matter is about 58% carbon. It's also made up of nitrogen and phosphorus, all the different other nutrients that exist and are important for plant health are in the soil organic matter. But when we're converting soil organic matter to carbon, it's about, 58%. So total soil carbon, and so we've got that 58% of organic matter is carbon, and then of that 58%, you've got the organic, and you've got the inorganic and elemental carbon as we go through the system. And it's important to look at the total organic carbon when we're thinking about soil carbon that's in the system. And that encompasses the carbon that's available now. So it's that carbon that's cycling really quickly and it's available for plant nutrients. And it's also the carbon that's maybe much further along the system, but can become available to the system as required. So that's why we think about total organic carbon. There's lots of mass and fractions and things like that you can do to convert. If you've got, say, a soil organic matter content for your soil, you can convert that to how much organic carbon you've got, or if you've got your organic carbon percent, you can then convert it to how much organic matter you've got. So that's something that you can do. There's lots of really great resources out there on soil carbon, and these slides will be made available for you, so you can have access to those links talking a lot more about it. So soil organic matter and soil biology are really, really closely linked. The soil organic matter helps support the soil structure, prevent the loss of nutrients in soil, and it's also really importantly a food source for our soil biology. So if we're declining our soil organic matter, then we're declining our food source for our biological organisms, and our biological activity can decline in the system. So when we're thinking about soil biology, that's the second part of the soil health guide. We're thinking about a huge range of organisms. We've got our tiny bacteria and our fungi, and then we've got our larger things in the soil. When we think about soil biology, it can be broken up into three main categories. We've got our ecosystem engineers, so that's our ants, our termites, our earthworms. They're altering the physical structure of our soil. They're helping break up the large organic matter bits. They're helping move the organic matter deeper into the soil. And they're also creating those pores for where the soil, the roots and the water can move throughout the system. So we've then got our litter transformers, and they're the ones that are breaking up those plant residues and also breaking up other soil bugs to make things smaller for our microbes. They are helping increase the surface area of the organic matter, which can increase the nutrient cycling. Then we get to our tiny ones. So these are our micro food web processes, so our soil microbes, our bacteria, our fungi. And these are really important because they're transforming the energy from one organism to another. So they're the ones that are helping, really importantly, part of the nutrient cycling conversions, and also forming beneficial relationships with plants through the binding of nitrogen and phosphorus. They're also really important in soil structure in terms of our fungi, because it sends through a hyphal network which can help hold the soil together and breaking down toxins. I went into my compost today and pulled out some of my compost, and it's looking really good, and I could easily find some of the, well, they're hiding now, but anyway, got some great earthworms in my compost. So I've got a good system, and that's a good way that you can test. You can dig a hole in the ground and have a look what's going on. What can you see? In terms of soil biology, I've got a short video here which we can play to kind of look through and demonstrate kind of what's going on deeper, since we can't unfortunately be in a paddock together. So we've got our plant bacteria, our plant material that's decomposing, and then we've got the organisms that help decompose that matter. We're then getting to our slightly smaller organisms, which are starting to consume some more of that decomposed plant matter. And then we go even smaller into our networks of our fungi, which is covering all the bits of soil. they're decomposing things, and as they do that, some of the carbon dioxide is lost for the system. Then we've got our bacteria and our really microscopic soil biology, which are actively working through on the soil surface and being involved in a lot of that nutrient transformations. How fast that decomposition happens, as we talked about earlier, a lot of it's determined by the climatic conditions, so the heat as well as the temperature. So that's a great little animation just looking at what's kind of going on. So in terms of thinking about our soil biology, having a big diversity of our species is really important, because we want to have those earth movers, we want to have the decomposers, we want to have the nutrient converters, we want to have all of them there contributing to our soil system cycling. So the important thing is the diversity in the food, so the diversity in what we're putting into the soil in terms of having a broad range of crops and a broad range of pasture species. All those different foods for the soil help promote a variety of the different soil biological organisms. So in a functioning ecosystem, you've got lots of different inputs helping feed all the different biological organisms. So we want to have that broad diversity in our what we're planting into the soil, which can feed the biology. So this is a commonly thrown around fact there, that we've got in 1 gram of soil, we've got what number of different species and what number of different individuals. So if you want to have a think about if you can guess what that is, that would be great. Feel free to pop it in the chat as well, in terms of the species and individuals. Yeah, we've got a number with lots and lots of zeros there. Got 10 billion. So we're pretty much, we're pretty close to it, maybe not quite that much in 1 gram of soil, but definitely across the soil, there's all of those. So in 1 gram of soil, we've got about 100,000 different species of biological organisms and 10 million different individuals. So that's phenomenal. That just shows how much soil biology is and how important it is to look after them. The next soil health factor is soil colour. So I love soil colour. I love that you can use it to be creative, to paint and all those different things. But it's also a really useful feature for us to help identify and describe and learn a little bit about what's going on in the soil. So the soil colour is directly related to the parent material. It can give us a good indication of the chemical properties of the soil and how well that soil is aerated or drained, and how much organic matter there is. And remember, we talked about earlier, there's the stuff in the soil and the spaces, and the soil colour is all about the spaces. How much air do we have in the system? We need air to the soil biological organisms to breathe. We need air so that there is pockets for the roots and everything to grow and move down the soil. So air is really important, and the colour of the soil can help determine that. It can also help us look at the different horizons as we move down the soil. So in terms of colour, you've got our black soils. So these are often rich in humus and they're often really fertile. We've got our brown soils. So that indicates that there's organic matter in the system and often also relatively fertile. We've then got our paler soils. So this indicates to us that there's lower levels of organic matter and clay minerals, and they're often less fertile. So if we think about, I guess, a compost or a really healthy, dark, rich soil, if that's really pale, there's a lot of that organic matter is lost in the soil. When we're thinking about the difference between the reds and the yellows and the greys, a red soil is a really well-drained soil, and it's high in clay and iron, and the yellow soils are the moderately drained soils, and the grey soils are the poorly drained soils. So we can look at the bottom here. We've got, this is deep in a subsoil. We've got some areas where there's yellow and some areas where they're red. What's happening is the iron in the soil is able to react with the oxygen and create iron oxide, which is essentially rusting. So that's why we're seeing the red. So that's giving us an indication that there's a lot of air and a lot of good drainage, so the water isn't filling up all those air pockets and taking away the oxygen, and so we can get that red color. When we're going to the yellow colors, the iron isn't as easily able to oxidize because there's less air around for the iron to be able to react, and so we're getting some of those yellow colors. Sorry, cars, because I've got that photo up there of a rusty old tractor in a paddock. So that's exactly what's happening to our soil. So when we're looking at the color of the soil, it can help give us an indication of what's going on. When I mentioned the kind of the grey, or those really you know, the blues and the greens as well, this really indicates to us that there's really a lot of waterlogging issues, and a lot of times in the year where those soils would be under wet conditions, because the iron isn't able to oxidize really at all, and then we get these colors in the soil. The next soil health factor is pH. So pH is not something that is only for the soil. It's something that's part of all the different things that we consume, that we work with, because it's essentially a measure of the acidity and the alkalinity of something. So we've got the pH scale, which goes from 0 to 14. And so I want you to throw in the chat some household products or foods that you can think of that might be either acidic or alkaline. So yeah, have a think about what is around and what there might be. Soap. So putting soap down as alkaline, are we? Ammonia alkaline. Yes, citrus and tomatoes, acidic, that's a good one. You either know that if you get an upset tummy by eating those, or you can taste the acidicness. Bicarb alkaline vinegar. That's great. So there is a huge variety of pHs in the products that we use. So we're thinking right down the extremely acidic conditions here. We've got our battery acid. Then lemon juice is pretty acidic itself. Bananas, they're acidic. There we go. That might be a new one for you. Wine vinegar. There we go. Good wine is acidic. Yes, probably on this side. And then we're getting to our more neutral pHs. So it's milk and water. Pure water is a pH of 7, so that's neutral. And then we start getting into our alkaline products. Not a lot of these are super edible. A lot of these are our cleaning products and things like that, as we got mentioned earlier. But there you go. Egg white is an alkaline substance. So when we're thinking specifically of soil pH, it's the measure of acidity or alkalinity of the soil. And this only dawned on me really recently why you actually say pH. pH, everyone knows pH is a thing. Why is it pH? So it's the potential of the hydrogen in the soil, because it's all about the concentration of hydrogen or iron. So there you go. There's a little fun fact that's ever comes up in a trivia. It's the potential of hydrogen. That's how we get our pH. So that's that same range of pH from 0 to 14 is in the soil as well. Another thing that's important about the pH scale is that it's logarithmic. So what that means is that when we move from, say, a pH of 6 to a pH of 7, the pH of 6 is actually 10 times more acidic than the pH of 7. So it's not just 1 times more acidic, it's 10 times. When we move from a pH of 5 to a pH of 7, that is 10 times 10, which is 100. So pH of 5 is 100 times more acidic than a pH of 7. So that's why measuring pH, and when you see pH numbers, they're often, if you get a lab report, 7.2 or 5.8, because when we're moving between the pHs, it's a significant increase in the soil. conditions. So why is pH important? And how can we understand the pH? So pH acidification is a natural process that's happening as part of the weathering. So our soils are naturally over time becoming slightly more acidic, and that's really linked to climate and temperature and rainfall. So this is a pH map of the state, and as we've got the yellows and the oranges being lower pH, which is more acidic, and as we move up the state, we get into our higher pHs, which is our alkaline conditions. So as you can see, as we move up the state, there is a significant pattern, and this is the surface pH. When we go to the deeper in the soil, we can see that same pattern exists, but conditions are less acidic in the subsoil. Also, we can influence the pH by our farming activities. So we can either increase the rate of acidification of the soil, or we can slow that down in managing the soil. So in terms of how we can actually measure the soil, there's three ways. There's pH in water, which is pH 1 to 5, soil water, and then there's pH in calcium chloride. So if you're getting a soil test done, these are the two pHs that they do in the soil. Why do we have the two different pHs? That's because, or two different ways that we can test for pH. That's because they're measuring the different processes about how they're measured, and they give us different indications for different conditions. So a pH in calcium chloride is a pH that is more consistent, so it doesn't change as much throughout the season. It's probably a bit closer to what the soil would be experiencing in summer. And it's a really good test for monitoring acidification. In terms of pH in water, it's a bit closer to the soil pH in winter, and there's a lot of data that's been done in this method of testing, so it's really reliable to understand what a pH is and what effect it has on plants. And they have different critical levels of where you want to be keeping a pH above. So that's important to know as well. Then we've got the ways that we can measure pH ourselves. So that's by doing a field test, by either one of the soil products that we can use to measure the soil pH by putting a dye and an indicator on, or we can use a probe as well. So I've got a little video here, but just in the interest of time, I'll just send you the link to that one, and that can be something that you can watch if you're interested about how would you actually do this pH testing yourself at home. So why is soil pH important, and why does it actually matter? Well, it matters because the pH of the soil is really significantly linked to how available different nutrients are in the soil. So in really acidic conditions or really alkaline conditions, so the extremes of the pH scale, different nutrients get tied up or released into the soil. And that's because there's a lot of chemical transactions happening. So for example, in really acidic conditions, we've got a lot of tie-up of the nitrogen, the phosphorus, the potassium, sulfur, calcium, and magnesium. So a lot of those nutrients are actually just being bound by the soil and not available for plants. So that's important because we want those nutrients to be available and not actually held tightly by the soil. In terms of, we can get excess nutrients as well. So in really acidic conditions, there's a lot of iron that can be released into the soil: manganese, boron, copper, zinc, and aluminium. And some of these are going to inhibit plant growth, especially aluminium. So in really, really high acidic conditions, so really low pH, there's a lot of aluminium in the system, which strongly affects plant growth. And that can be seen the same as well in alkaline conditions. You can have some of these nutrients being tied up that we do want to have available for plants. So that's can have too much or not enough. Also, our plant roots are sensitive as well. So like our hand, we don't want to put our hand into a really acidic condition or, into drain cleaner or things like that. plant roots are no different. They're sensitive to pH as well. So they want to have as close as you can to a neutral pH. And not only is it the plant roots, but soil microbial activity is strongly affected by pH as well. So they don't want their conditions too alkaline or too acidic. Plants, as we talked about the roots of plants, there's different plants that have different tolerances to different pHs. So you've got the pasture species and the crop species that are more sensitive to pH, which means the range that they're going to be more productive is smaller. And then you've got some of the plants that are more tolerant to pH conditions. So for example, your perennial rye can tolerate a pH, this is pH in water, of 5 to 6.5. That's where its ideal conditions are. But for example, a medic here only wants to be in a pH of 6. So pH of 5 would be too acidic for this pasture. I like to do the analogy of blueberries. So blueberries are something that's really different to a lot of crops and pastures, is that they actually like really acidic conditions. So this will be a bit hard over the video, but I've got 2 blueberries. I'm not going to be able to see them easily because of my background, but this is a blueberry that I've planted that's in a really high, this is a really acidic condition, so really low pH, and it's thriving. And then I've got a blueberry which is planted, so it's much smaller, and this is in a really alkaline condition. So different plants have different preferences for how they want to grow in their pH. So what can we do? How can we help with acidic conditions? We want to reduce the hydrogen in the soil. So lime is often used, which absorbs the hydrogen that's sitting in the soil and helps neutralize the soil. We can also reduce the leaching of nitrates, because when nitrates leach out of the soil, they actually take the alkaline cations in the soil with them. So not only are you losing your nitrogen, but you're also losing the alkalinity in the soil, which makes it more acidic. So we want to make sure that we're utilizing that, and we can influence that by the fertilizer or amendments that we're putting on and matching them to the productivity of the system as well. And as well, we can help with acidity by choosing plant species that are going to have the correct amount of tolerance for what we're growing. The next soil health factor is soil texture. So I don't know who else out there liked making mud pies as a kid. I definitely loved doing it. But that's what soil texture is. It's all about the feel of the soil. So it's about how much clay is in the soil, how heavy it is. You know, we all know what clay feels like. And then we've got our sands, you know, which are really different texture. So that's what texture is. It's the feel of the soil. Well, why does that matter, and what can we learn from that? So when we're thinking of soil texture, it's the proportion, it's of how much sand, silt and clay there is in the soil. And as we can see here, sands, these are really large in size. So they take up a lot of space in the soil. We've then got our silts, which are the next size down, and then we've got our clays, which are really, really tiny. So the proportion of these in the soil affects how much water and nutrients that can be held, and influence those spaces that we talked about in the soil. Because if you've got lots of big clumpy bits of sand, you know, we all know what a sandy soil is like. It doesn't really hold much water because there's no ability for the soil to be bound together, and so there's lots of spaces of air but not much water can be held. And clay is really important in our soils, because clay, even though it's the really, really tiny small little fraction there, clay, because of the makeup of clay, it has the ability to attract nutrients and attract water and attract soil to itself. So it's really important because of the charge of clay and the makeup of clay. It's what's helping bind everything together. So the downside of if you have way too much clay in a soil, those clay particles, because they're so small, sit really closely together, and then you get you don't have enough spaces for the water and the air to move. So you've got poor drainage and poor aeration. So that's why sandy loams, clay loams, there are our ideal soil texture, because they're a good balance of everything there. There's also maps of soil texture that are done across the state. So as we've got our sands up here, as we get further south, we've got more clay in our topsoils, and then this is the subsoil as well. So a lot of heavy clays in our across Victoria. So how can you do this yourself at home? So you can get the soil, you can get it in your hands, and you can essentially try and see how well it sticks together. I've got another video for that one, and I'll just pop that in the chat. So that's another one that you can watch in your own time about how you can assess the texture. But like I said, it's that feel of doing it, and how well it sticks together. So the next soil health factor is looking at topsoil. So topsoil is really important because it's the most organic, rich layer of the soil. It's where a lot of the soil organic matter is sitting. It's where a lot of the roots are. It's where a lot of the water is in the soil, and therefore we need to just make sure that we're looking after our topsoil as best as we can. And the deeper that topsoil that we have, the higher reserve that we have for holding on to the nutrients, holding on to the water as well. And we can influence that by our management practices and how well we're looking after the soil and putting inputs into the system in terms of roots and having good ground cover and things like that to keep the soil growing. So I don't know if anyone out there knows how deep their topsoil is, but it's an important thing to think about. How deep is that soil, and how much activity do we have in space for all of that important nutrient and organisms and things like that to exist in the soil? So you can understand that by digging a little hole and just seeing that point of where you can distinguish between the topsoil and what's going deeper. The next important soil health factor is soil structure. So the soil structure is about how the stuff that in the soil arranges or holds itself together. This is really important because this allows us, as with the texture, in terms of how much sand, how much silt, how much clay and organic matter is in the soil. This is about how it all binds together. So when all those particles bind together, we get aggregates. And it's the electrical properties that are found in clay and the organic matter that we talked about earlier, the way that clay functions that can bind the soil together. And the soil structure, when we're thinking about the structure, is the arrangement of how those aggregates have been formed together. So this is important because this determines how much air and water there is and how the roots will be able to move. Because the soil requires these pore spaces. We need the big pores, which are called the macro pores, and this is the spaces between the aggregates. And this is important for drainage, aeration, and root growth. So this is where our roots are going to be growing. They're going to be growing down these gaps. This is where the water is going to be moving out of the system, and where there's good air for everything to be able to cycle. So we've got our macro pores, and then we've got our micro pores. So these are the ones that are inside those aggregates, that are in between the clay, the silt, the organic matter, the sand, in between those. And they're important because that's where water and nutrients will be stored for the plants to access later. So it's really important that we've got really good aggregation in our soil, so that we can have good movement of water, air, and the transformation of nutrients. Soil biology is really important in this, and we saw that earlier in the video that we watched, where the fungal hyphae can grow all around the soil and all through the soil and hold it together. So really important that we don't disturb the soil as much as we can to allow those processes in place to hold the soil well together. So this is an example of a poorly structured soil. where everything's packed really tightly together. And this is a well-structured soil. So you can clearly see the difference here. There's not the spaces for the water and air to move, where here there's a lot more of that. This is quite a fun way to be able to test how your soil structure is to dig out, say, a 20 centimetre deep by 20 centimetre cube of soil, and then you pick it up, you take it to about your waist, you try and hold it together, take it to your waist. I'm quite short, which you can't tell because we're doing this virtually, so I probably need to lift it a bit higher, but then you just drop it to the ground. So as it drops and breaks, those aggregates start to fall apart, and we do that a few times with the different clumps, and then we can see how the soil is structured. So this example up here, this is a really poorly structured soil because it's way too tightly compacted, and there's really hard for the plants and roots to actually access everything that's going on inside those clods or pieces of the soil. As we move down to a really good structured soil, here we can see there's lots of small aggregates, which is great, and a really good amount of spaces for the plants to be able to move, and the air and the nutrients. So that's how we can test for soil structure. Really strongly related to soil structure is soil compaction. And so this is how the soil structure is being held in the soil. So whether it's compressed or whether it's as it would be able to be in a non-compacted state. So we can see soil compaction when you get heavy machinery which runs across the soil surface, especially when it's moist and squashes all the air particles out. But that's, yeah, if we're not managing how we're driving over our soil, we can cause compaction. We can also cause compaction such as equipment that we're putting into the soil, which is constantly compressing the soil as it moves through the soil, or animal movements as well. So if we've got lots and lots of, say you've got all your cattle in a paddock and they're all camping in one area and the soil is really wet, what those hooves are going to be doing is compacting the soil. So how we think about our animals moving across the farm and a machinery can help reduce compaction. And how we understand compaction is bulk density. So you can do lots of soil sampling to understand bulk density, but another way to do that is soil penetrometer resistance. So you don't need a fancy penetrometer. You can just get any kind of metal rod and push it into the soil and see how well it moves down. So as you can see here, this is on a wheel track. The rod doesn't go easily into the soil, but where there is no wheel tracks, where the soil hasn't compressed, it's easily able to move down. Another way is looking at the soil. So we can try and look for these kind of really compacted layers in the soil, like this one here, where we can see a really compressed, really tight bit of soil. So no roots are going to be growing in here. All the nutrients, all the water, everything that's held in here isn't accessible to the plant, so it's no use. Plant roots can also, because they're the ones that are doing all the hard work moving through the soil, are going to be the ones that are going to tell us what's going on. So if this is a canola, or no, this might be a lucerne, I think, but canola, lucerne, anything that has a big tap root, pull out a plant, have a look what the roots are doing. If the roots are growing down straight, if they've got lots of bits of soil connected to them, that's great. They've got good aggregation in the soil, the roots are happy, and if you pull out something that looks like this, well, you've clearly got some compaction because the roots aren't able to grow straight down as they'd like. They're going to grow around those compacted layers. The last soil health factor is how stable the soil is when it's wet. So when soil gets wet, the water is going to be moving at a high pressure past those soil aggregates. So what we want to understand is, in wet conditions, when it's raining and when the water is moving through our soil, how stable is that? How well is our soil going to hold together and those aggregates bind? So what we don't want to see is slaking and dispersion. So what is the slaking? So slaking is where those aggregates that we talked about begin to break down when the soil gets wet. And what that means is that we can have those macropores, so those big gaps in the soil between the aggregates, can start getting blocked, and we start losing functionality in our soil in terms of water and air movement. Organic matter is really good at reducing slaking because it helps bind the soil together. And this is, yeah, so we've got our aggregate here and it begins to break down and we start seeing slaking. I will show this video, it's quite a short one, and he's quite an entertaining guy from the US. So hopefully the sound will come through and you'll all be able to watch this. And this is how we can test for slaking of our soils. So if someone could give me a thumbs up or something when it starts speaking so I know that you can hear it.
We don't have to seem to have sound back.
Oh, okay, well that's okay. I'll just talk through it and we can see what happens. So 2 soils, the same soil type. That's a soil that's been tilled, and that soil hasn't been tilled. So we're going to see what happens when we drop them in. So the one on the left is the tilled soil. It's falling apart. Everything is breaking away. There's no soil pores. It's a shame you couldn't hear the guy. He's a character, but I will pop the link into the chat. But yes, as you can see, when the soil can withstand the pressure of water and move and hold on to itself, we see it being really stable. And so that's the difference of management practices can have in reducing the slaking of the soil. The next stage of the soil is dispersion. So this is a chemical process. So this is where the clay particles, so those tiny, tiny little particles in the soil, actually move out of the aggregates themselves. So slaking is where the aggregates fall apart, and dispersion is where those aggregates that have already moved away from each other then begin to essentially disintegrate, and the clay moves all through the soil, and that's why we can see really cloudy soil there, because the clay particles have repelled and are suspended in the water. So this is usually because we've got a lot of sodium in the soil. Sodium, this is very fuzzy, so sorry about that, but the sodium in the soil, when it gets wet, it attracts lots and lots of water. So those sodium particles that are sitting on the surface of the clay just take lots and lots of water and swell. So what that swelling does is it separates the clay plates from each other and they become dispersed and suspended in the water. When we don't have lots and lots of sodium in the soil and we've got more calcium in the soil, the calcium isn't as hungry for water or as greedy at taking the water and doesn't swell. So it doesn't push those soil clay particles away from each other. What that means is that we want to be having more of the calcium in the soil than the sodium. And I'll pop another video in the chat that talks a lot about dispersion. Dispersive soils are really bad because they, when those clay particles have been moved out of the aggregates, when the water recedes and you've lost the moisture in the soil, those clay particles have filled lots of the pores and the gaps in the soil. So you can get the surface crusting, which affects how the plants are going to be able to grow. It also affects the aeration because you've blocked up some of the pores as well, and you get increased runoff and erosion risks as well. And there's less air and water available for the microbial activity to continue. And one way to manage dispersive soils is to apply gypsum, which knocks out the sodium in the soil and replaces it with a calcium, so holds the soil together. Soils are often dispersive or sodic at depth, and so it's really important to, if you are going to be doing something that interacts with your deeper subsoil, to make sure that you aren't going to be taking bad sodic soil from at depth and bringing it up to the top. So it's really important to understand if your soil is sodic or not. And you can easily do that by getting a piece of soil, one of the little aggregates, and popping it into some water and just seeing what it does and seeing if it does disperse or does hold itself together. So that's essentially a really quick rundown of the Soil Health Guide, looking at cover, biological activity, ground cover, pH, texture, topsoil and structure, compaction, and slaking and dispersion. So that's a soil health guide, and thinking about soil health indicators is one way of understanding what's going on in our soils, but another way is soil testing as well. So the next part of this chat will be talking about soil testing. So who undertakes soil testing on their farm, or who's going to be undertaking soil testing? So feel free to pop in the chat your soil testing. Yeah, that's great. So we've got some people who have just started to undertake it, or interested in it, or actually doing soil testing. So that's fantastic. So hopefully the next session will be useful for you and can help you think about, you know, how you can use those soil tests to understand what's going on. If you haven't started doing soil testing, then this might give you a bit of a encouragement to think about how soil testing could fit into your farm.
Soil testing is a really important decision-making tool. We use it to determine soil nutrient levels and other soil characteristics. The tools you'll need is a soil corer, a clean plastic bucket, a plastic bag to put your samples in, a tray to do your sub-sampling, and an aerial photo or mud map will assist with the planning of that soil sampling. The other really important factor is to make sure that your soil corer is 10 centimetres and take the time to measure it. An aerial photo can be used in planning where to take your soil test. Areas we don't do are around water troughs, around gateways, within 4 metres of a fence line, and other clearly different areas within the paddock. So within this gully here, we're not going to take a sample. And also a stock camp up the top of the hill. Once we determine that, it's very easy to work out where we're going to put our transect. And in this case, we'd look at a transect along there, and then also one back that way. That would give a truly representative soil sample of this paddock. I've got that end tree as my end point as a transect, so that's what I'm heading towards. This has an internal taper, so it always taps out backwards, and you just make sure that it's totally clear before you take the next sample. So this is a 300 metre transect that I've got off the aerial map, so that means I need to take a sample every 10 metres to get 30 samples. We've got a urine patch and a cow pat there, so we're not going to test there. So we just move off to the side on the same transect, take a sample. Once we've brought our 25 to 30 cores back, we put them in the bucket. We need to mix them thoroughly, and to do that we'll pour them out in this tray and break up all of these cores. While we're doing this, we'll remove any vegetation matter and rocks. Once we're happy that we've sampled that and we've got a really consistent mix throughout, we're going to what's called sub-sample. We break that in half. and then we'll break this section here in half again. You want to end up with about 200 to 300 grams of soil to put in the bag. Once we've got that sample, it's really important that you've got your name, your address, your paddock name, and the date at which you took the sample. Samples should be placed in laboratory supplied bags for postage. The soil test results are going to come back to you in a range of different formats. Use your local agronomists, Landcare groups, or departmental staff to assist you with the interpretation. It's really important that we use this information to make informed decisions on what you're going to do with your soil and make sure that they align with your overall farm goals.
Well, hopefully that was useful or interesting or new for some of you. So yeah, there's a lot of planning that has to go into thinking about where you want to be soil testing. So just looking at some of the questions. So is there a rule of thumb % for soil organic matter? So one of the next sessions that we'll hopefully be able to run for you guys is how to understand and interpret the soil test. So we'll go into depth about soil organic matter, but in terms of how much soil organic matter, it really depends on, I guess, farming type. So whether it's, in grazing or if it's cropping, or as well, if it's in a high or a low rainfall zone. So I can send through the kind of information that's relating to a lot of those different factors. Slow one be eucalyptus leaves. Yeah, so I don't know about you guys. Yes, my compost, the eucalyptus leaves often take a while to decompose. A lot of that can be due to their chemical makeup as well, and being repelled by some soil biological organisms, so they can take a bit longer. Can you have too much soil organic matter? Not really. So the soil organic matter is usually going to be around about that, say, 3 to 6 to maybe 10, if you've got a lot of great stuff going on in the system. And so it's never going to be a hugely dominant part in the soil, but it's really important in terms of the nutrients and the carbon and all the stuff that we discussed. So there's not a point where there's too much soil organic matter. One little thing to note though as well is soil organic matter itself is inherently slightly acidic. So if we are increasing our organic matter significantly in the soil, which is a great thing to do, we will also be slightly increasing our acidity in the soil. So that's just something to keep on top of. Just scrolling down to any more questions. Oh, here we go. Danny's putting together. Yes, and so you can do pH testing of the plants as well, but that's different, I guess, to the pH testing of the soil. So they're slightly different, and a lot of the stuff and levels that I talked about is specifically to the soil, but yes, you can test the plants themselves.